DIWA in the regulation says the following. You can only build up systems up to 1000 volt DC. So your electrical configuration, right, as I told you guys before, right? Let me just make another panel here. This is the cell number 1. This is the cell 72, okay? Each one has 0.6 volts. Then after combined in series and in parallel, we will have a 45.8 volt. All right, this is VOC, okay? So the challenge that we have now, and now you guys starting understanding the modularity of the system. And the modularity of the system goes like this. The people that manufacture your panel, they know that they have to compute 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 maybe in series, right? To have the escalation of 0.6 to another level of voltage, all right? And then putting in parallel to be able to build up current. So we as a solar industry people, we also do the same exercise, but we don't do it in the cell level. We do it in a module, solar module level, okay? So we know that we cannot show to DIWA that your system is 1300 volt. We cannot do that, right? At the same time, DIWA has other restrictions, but the more important for you to understand is this one is just to standard and make sure that you know that your system, your solar system here in this project does not cross 1000 volts, all right? So now you tell me one thing. If I tell you that our electrical setup, panels in series and therefore in parallel and all that stuff, you know, then you will be able to tell me how many numbers of panels I do have in a series, all right? So let me try to do this a different way. Can you please divide it 1000 volt DC by 45.8 volts VDC, volt DC? How much it goes? 21.8 solar panels, right? If this is the characteristics of one module, right, then if my limit of DIWA is 1000 volt, I cannot cross it, then the maximum amount of numbers of panels in a series, right, will be 21.8, all right? Of course, we cannot cut a panel into 3/4 or 80% and then install it, right? Or we should take a decision, or we go 22, or we go 20, or 21. Could be 21, right? All right. So if you look into this number, it gives us a couple of solutions. So if I go 22, if I go 22, I'll be 1000 volts above. So DIWA will reject my design, right? But they should allow me to go 22 or even lower. I can go 18, 19, 17, right? You will see there is a restriction on that end, right? So, or 20, right? Anyhow, we need to account also for energy loss, right? In terms of temperatures, right? We know very well that voltage and current both are affected by degrees Celsius, all right? So during our design, we know and we specify the design temperatures, all right? T cell could be 80 degrees, right? As a maximum. T minimum, T amp, right, can go 0 degrees, all right? So what are we saying is this? We are saying that our temperature, this is ambient temperature. Our ambient temperature can reach 80 degrees and our ambient temperature can reach 0 degrees in this location. Of course, this is always design assumptions. We will never reach 80 degrees ambient temperature. It's less likely that you reach 0 degrees as well, right? I think you'll never reach 0 degrees here, right? Okay, so our system our voltage, the numbers of panels in a series should be able to understand and should be able to withstand and work under these operations, all right? But we know that these limits affect voltage and current, all right? Without further delay, I would say that your system in the project accounted for the temperature coefficients, energy loss, voltage loss. We went for a 20 in series, all right? And this has been approved by DIO, all right? Okay, some electrical general stuff that I would like to share with you. In a DC circuit, right, if we do a connection of series, what's going to happen with my voltage? We will sum the voltage, right? This is for voltage. What will happen to the current? The current will remain the same, okay? So it makes equals, okay? In a parallel connection, you may see where this takes us. This is the opposite, all right? So let me just make one more sketch here for you. Now I told you guys, we have 20 panels in a string. I will define a string for you in this next schematic. Panel 1, plus and minus, blah, blah, blah. Panel 20, plus and minus. All right? And we know that this is 45.8 volt and current of 9 point something? 9.8, let's say 9.8, right? Amps, okay? So each panel, open circuit voltage, has a 45.8 and a short circuit of 9.8 amps. This is physics. No one changes this. No one changes this. And this has been certified by these third-party guys, all right? That's why you buy the panels, because someone told you can buy these guys, okay? Because we trust their technical sheet. So now, what we are doing is that on the second panel, that is here in the middle, okay, which has a plus and a minus, this positive will keep loose, okay? And then we connect this one with this one. Then we go, this one is this one, until the end. So I have a positive loose here, and then if you do these connections, this one will be connected to the other, and I have another loose here, right? Loose again. So what I'm having a negative here and a positive here. And this is what we call a string. String of solar panels.
So this is a series connection.
This is a series connection, yes. And how we did this, right? Now, can you make this calculation for me? Now I have the 45.8 on each unit times the 20 panels. How far it goes? 9? 963 volts.
No, 1.6,
sorry. Okay. 916 volts. Okay? So, under the previous conditions of irradiance and temperature, if you come with your meter under that conditions, in this positive and negative, if you put your meter here, voltage DC measurement, you'll be able to get this. All right? Now, you guys remember also that in a series connection, the current does stay the same. So if I have 9.8, even if I have 20 panels in the series, my outcome will be 9.8 amps. Okay? And this is what we call a string. Okay? And this is below DIO requirements. But in the future, maybe if the regulation change, there are systems that goes up to 1,500. Okay? Okay. So, now we identify our string. I will make a small schematic now, okay, of our string here. Panel 1, panel 20, okay. We have a cable here. We have a cable here. Here's a plus and a minus. Okay, this is the electrical circuit. Okay? And then I will add now an inverter. And the inverters are the machines that you have in the old archive room and in the factory. These big noisy machines, right? So these machines are also rated by a technical sheet, okay? And the ones that we have on this project are called PVS 100 from ABB, okay? Which means that they have a 100 kilowatt AC output, okay? So what's going to happen now? Now, since we build up the panels in series together in the roof and there are 1 plus and 1 minus left over, we bring these 1 plus and 1 minus up to the inverter. That's what the schematic represents here, right? The inverter has a DC side and the inverter has an AC side, okay? So the DC side comes here and we connect here, all right? So at this moment, we have here our open circuit voltage conditions, okay? And then on this side, we have the DIWA side, correct? Okay, so now I'll add another schematic here. This is what we call, let's say, a combiner, big breaker here, that goes to the DIWA, okay? Okay, so in the roof, since your project is so big, right? In the roof, we have multiple of these, right? We have multiple strings. We have 200 and... So our total number of strings equals to 234. So in the roof, we have 224 replications of these sets, all right? So now if you multiply 224 by the 20 panels in series, you will have the maximum amount of panels that you have installed in your roof, 4,280. So you have 4,200 panels, 80 panels over there, and they are electrical bonded in the strings of series of 20, okay? And each string has to go and deliver something somewhere. And that goes to your inverters. This is inverter 1, and then we have multiple inverters as well, as you know. And we have the last one, number 13. Okay? But all of them are the same. All right? Okay. Now, think with me. We decided, well, better, we specify before, let me just delete this one here. Okay. Doesn't matter. Okay, so now, in the previous slide, we specify how it is our volt. Okay, fine. So 9, let's do one thing so you get this clean later in the future. Okay, now 916, right? Volt, okay. This is voltage, this is amps, and we know that each panel is, remember this, what peak? Yeah? Okay, so if I multiply this by this, all right, I should be able to get somewhere to that. That's mathematics, correct? And then, if I multiply by the number of panel indices, I know that each string will have certain amount of power. Okay, now, I have 325 watt peak per panel into 20, right? How much it goes? So it will go 6,000, 6,000 and a quarter, 6,500? 6.5 kilowatts? Okay, 6,500 watt peak, okay? So we have this condition, and this condition, all right? Now we're going back. Keep this number in your head, okay? Now we know here that this machine is 100 kilowatt AC. It can generate 100 kilowatt outgoing of the machine. If you divide this machine by this rated power by the maximum string value, right? Is the maximum value I can have on a string in the best conditions possible is 6.5 kilowatts. So if I divide 100 by 6.5, how much it goes? 15.38. All right? Numbers. Okay? So means what? Means that I can, if I want to match the same rated power AC with the DC, I have to install in this, I have to bring, this is step number 1, 2, 3, 4, 5, 15. See the 15? I have to put 15 there. 15, I cannot break down the string, right? I could, but it's not advisable. So we have to go for 14 or 15. Or we go 14, or we jump to 16, right? You will see the number that we build up later, okay? So, but that's how we make sure that we receive an X amount of energy here, power, and then making sure that the inverter runs the game and converts DC to AC, and therefore we put it here in this bus, okay? All right, so series connection, all right, internally the machine, what we're going to do is they will parallel it. All this current means the voltage and the amps are coming here. They will be paralleled here, so they can build it up. Voltage will, in this case, remain the same, and current will be multiplied, right? So your 9.8 amps that you have here, you remember you have 9.8 amps, all right? Here it will be paralleled. So 9.8 times 15 in these conditions, 15 in series, will be the amount of current you have inside the machine. And that current will be therefore filtered, leveled, oscillated to be able to produce your three-phase system. This is a single phase only, but three-phase system. Okay? Something like this. All right? And the other curve will come like this. So this is a three-phase system. 1, 2, and 3. Okay? And the machine will do that. It's totally automatic. You don't have to touch a button. Okay? So, series connection, parallel connection inside. Then we have again here an outgoing here, L1, L2, and L3 going into your cable, sectioning here on a breaker. And here we have another bus bars. Right? Phase 1, phase 2, phase 3. All right? You could have one more neutral, but these inverters are 3-pole only. All right? So then, this breaker also, the main breaker is also hooked here, phase 1, phase 2, and phase 3. Okay? And here, what are we doing? We are doing parallel connections again. Right? And therefore, when we reach DIWA, all right, then we will have all the energy that we produced on not only inverter 1, but in the total amount of the inverters. Okay? Okay, so let's jump to the last piece of the game. Okay, now we have your big AC combiner with multiple small breakers. So in your project we have one with 9, so this is one, this could be number 9. Okay. And then we have a main breaker here, which we call it a motorized breaker. Okay. Then we have what we call a meter cabinet. All right. So let's make another enclosure here. So a meter cabinet. Okay. With an isolator again. Okay. And with the respective meter. And then we have the point of connection. All right. So we will see what is the details on your project. This is only schematic, okay? So current has been generated by the DC side, has been converted to AC, has been delivered here. There is the bus again, right? And then we take it from here. This is usually a 3-core or 4-core cable. And then you deliver into the meter cabinet.